Listen to part of a lecture in an engineering class.
Because every earthquake presents us with unique conditions, it's difficult to anticipate the stresses that'll ultimately affect the structures we design and build. So our challenge is to try to design a building that'll be as safe as possible for all types of earthquakes. Besides that, during the past decade, the expectations for earthquake-resistant structures have changed. Whereas in the past, it was considered adequate for a building not to collapse during an earthquake, now insurance companies and even clients, they're demanding buildings that'll be able to maintain their structural integrity through an earthquake and remain sound after the earthquake subsides. So in recent years, we've developed several techniques for building more earthquake-resistant structures. For relatively small buildings, all we have to do, really, is bolt the buildings to their foundations and provide some support walls. Remember, these walls are referred to as shear walls in your textbook. They're made of reinforced concrete, and by that I mean concrete with steel rods embedded in it. This not only strengthens the structure, but it also diminishes the forces that tend to shake a building during a quake. And in addition to the shear walls that surround a building, shear walls can be situated in the center of a building around an elevator shaft or a stairwell. This is really an excellent reinforcement. It's commonly known as a shear core, and it contains reinforced concrete too. Okay, let's talk about walls. Walls can also be reinforced using a technique called cross-bracing. Imagine steel beams that cross diagonally from the ceiling to the floor, and this happens on each story in a building. So before the walls are finished, you can see a vertical row of steel X's on the structure. And this cross-bracing tends to make a building very rigid and consequently very strong. But besides steel reinforcements, engineers have also devised base isolators, which are positioned below the building, and their purpose is to absorb the shock of the sideways shaking that can undermine a building and cause it to collapse. Most of the base isolators that are currently being used are made of alternating layers of steel and synthetic rubber. The steel is for strength, but the rubber absorbs shock waves. In higher buildings, a moat of flexible materials allows the building to sway during seismic activity, or large rubber cylinders support all of the corners of the building and in between each floor, and they allow the building to sway during an earthquake. So you can see that these alternatives are quite different from cross-bracing or shear walls. So the combination of reinforced structures and flexible materials has been proven to reduce earthquake damage. But even these engineering techniques are insufficient if the building's been constructed on filled ground. Soil used in fill dirt can lose its bearing strength when subjected to the shock waves of an earthquake, and the buildings constructed on it can literally disappear into the earth. So in areas where earthquakes are known to occur, it's important to understand the terrain, and you have to be sure that the ground's either solid or it's been adequately prepared. Okay, let's assume that we do everything right. We choose and prepare the construction site, and we design a building with plenty of reinforcements and flexible materials. With cross-bracing, we probably have a building with the strength to hold up under earthquakes, even those of relatively high magnitudes. And while this is great for the building, what about the occupants? Well, the structure may be strong, but the furniture will probably be overturned or shifted during the earthquake, and that could result in major injuries for the people inside. So, now that we've made progress in solving the problem of how to preserve the buildings, one of the more recent areas of research is how to better protect the occupants during an earthquake. One interesting possibility is to design buildings that house a series of pistons, and these pistons are filled with fluid and controlled by sensors in a computer. So, by analyzing signals from the sensors, the computer should be able to determine the magnitude of an earthquake in progress. And when it does that, it can trigger electromagnets in the pistons to increase or decrease the rigidity of the shock absorbers built into the structure. If the earthquake's minor, then the building can be programmed to sway gently, and the people and everything else inside get a safe ride. But during high-magnitude earthquakes, the shock absorbers can freeze the building to prevent it from shaking at all. So the beauty of the concept is that the computer sensors work very quickly, reacting within 1/1000th of a second. And they can run on battery power since the electrical system usually fails during an earthquake. Will the concept work? Well, the National Science Foundation is supporting more research into the potential of pistons. And the results so far are promising.